Dave, would you like to start?
So the mic is the camera, so you probably want to.
So welcome to ICNRG. We have a pretty full session this time, so we're going to be running with careful timing. We have a whole bunch of research talks, which will be the focus of the session. We won't be talking about drafts or progression of documents very much. So let me start.
We may have had an audio issue.
Can you hear me?
I'm getting a chat saying that there's an audio. Oh, hang on.
Do I need to start over? Oh dear.
We might need to start over.
All right.
Apologies.
Now that we have audio, I will start over. Sorry about that. Quickly, the IRTF has a different intellectual property policy from the IETF with some mostly the same things. Please check to make sure that you are following those rules, particularly if you're presenting in these sessions or submitting documents. We make audio and video recordings of all of the meetings, and by participating online or, of course, in the main room, you turn on your camera and microphone. By doing either of those, that is an implicit consent to appear in the recordings. The IETF has a privacy and code of conduct that you should be familiar with, please. If you have any doubts, please check the links on this slide. Now, in general, ICNRG is one of the research groups of the IRTF, and we are a research organization, not a standards development organization. We publish both informational experimental documents, but that's not our only goal. Our primary goal is to coordinate with the broad research community and collaborate with them on exploring research issues that are related to the internet. And there is a primer for IETF participants to understand how the IRTF has similarities to the way the IETF works and some differences. So please check that RFC if you're interested. The session's being recorded. The general tips, please sign in with MeetEcho. And for remote participants, please make sure your audio and video are off. unless you're actually presenting during the session. That will be ditto true of us as chairs. So that's the introduction material. What I'd like to note here is we have a new co-chair, Dirk Kutcher, who is now chair of the entire IETF, has been very careful about selecting a wonderful new co-chair who will introduce himself momentarily. And also thanks to Jinjiao Li, a student at Hong Kong University of Science and Technology, Shenzhen, who has agreed to be the note taker for our meeting. We do have a note taker website, and any of you are welcome, of course, to contribute to the notes, which I'll go over with Rio after the meeting before we get them published. So, Rio, over to you.
Maybe it's better if you come here. I don't know. All right. Hello, my name is Rio. I'm the new co-chair of the ICNRG. My main area of research has been network protocols, ICN, IPv6, mobility multi-homing, and all sorts. I'm currently a lecturer at the University of St. Andrews. I was previously a postdoc, which is when I started engaging with the ICNRG. So, can you pass the control over to me?
Just a second.
I'll just take back the control myself.
Yeah, you can take control.
There we go. All right. So without further ado, here's the agenda for today. We will then start with the talk from Kazuhisa Matsuzono on in-network retransmission controlling ICN. So let me switch over the slide. All right, and then I shall pass slide control. All right, over to you.
So he should turn on his.
Hello, can you hear me? Hello, can you hear me?
Yep, we can hear you just fine.
Okay, thank you. Okay, I'm Kazuhisa Matsuzono from NIST Japan. We revisited in-network retransmission scheme in ICN. So let me talk about this work. Sorry. Okay, so recently we've seen the growth of low latency and high quality video applications like 4K or higher quality real-time video streaming. So, for example, teleoperation of robots requires real-time video feedback from the publisher, which generally requires network boundaries of 10 to 100 megabps. And also another important aspect we need to consider is the end-to-end latency should be less than 200 megabps. So in order to enable the reliable and safety operations, it's important to recover data loss in the network. But it's so challenging because of this kind of latency requirement. So let's now consider the end-to-end end-to-end retransmission-based loss recovery, which is commonly used by such as TCP. So the publisher initiates data retransmission based on the feedback from the end consumer. So in the end-to-end case, the recovery delay is likely to be long. And in the hop-by-hop case, we call it in-network retransmission. The loss recovery is performed locally. So it's expected to accelerate loss recovery in the hop-by-hop case. So let's now consider ICN, which adopts a consumer-driven name-based communication. So this consumer specifies the latest data name to obtain the real-time data from the publisher. So in ICN, ICN-based communication supports in-network caching, which enables intermediate nodes to retransmit the lost data from the node cache. And also ICN supports hop-by-hop flow-aware transport, which enables intermediate nodes to perform in-network retransmission with consideration for application-specified latency requirement. So ICN can potentially accelerate in-network retransmission, but we need to consider how we can suppress the duplicated data transmission and while satisfying the latency requirement. So there are some technical considerations like how to detect loss, which intermediate node should send recovery interest, and when and how many times recovery interest should be transmitted. So basically, the challenge of this work is to deal with the trade-off between the network cost and the recovery delay. So in this context, we propose a in-network retransmission scheme in ICN. So let me briefly explain the key features. So the proposed scheme introduces a metric called recovery budget. So the total available recovery budget is determined by the application specifies acceptable latency and end-to-end propagation delay. So this consumer allocates available recovery budget to each link, so that each link can execute per link retransmission-based loss recovery. More specifically, the downstream node in this figure case, VL, the downstream node sends a recovery interest. So this interest is not related to further upstream nodes. It's only used for in this link. So based on the allocated budget to this link, the node upstream node switches between the two relay modes for recovery data. So one relay mode is stop and wait, where the received recovery data is not related to the downstream node. So this recovery data is related to downstream node only when receiving the recovery interest from the downstream node. So in this case, the duplicated data transmission is not likely to occur, but the recovery delay is likely to be long. So another relay mode is fast relay. In contrast, in this mode, the received recovery data is immediately relayed to the downstream node. So the recovery delay is likely to be low, but in this case, duplicate data reception is more likely to occur because after relaying the recovery data, if this node receives recovery interest from the downstream node, this upstream node will retransmit the data again. So as I mentioned, this consumer allocates available recovery budget to each link. So ideally, it's best for each link to perform stop and wait to avoid duplicated data reception, but it needs more recovery budget. So in such a case, total available recovery budget will run out. So which means this consumer cannot receive the recovery data within the specified acceptable latency. So so that's why this consumer collects two budget information. One is the budget consumption, and another is a budget request. Budget consumption means estimated recovery delay when obtaining the recovery data with a probability of over 99%. And the budget request means an estimated recovery delay when performing some stop and wait. So as we can see in this figure, the intermediate nodes put insert two budget information into the real-time data so that the consumer can collect the two budget information. Then
It looks like it might be a presenter issue, right? Because the other
Yeah.
keys, okay.
Could be a problem on Kazuhisa's side.
He's back.
Okay, it's back.
Can you hear us okay, Kazuhisa?
He has to get off mute.
Oh.
When he came back in, he must be muted.
The audio is still given to the individual. He still has audio rights, I think.
I'm looking.
What if I revoke and resume?
I wouldn't do that unless. I don't see him. Oh, here he is. Yeah,
It says audio published.
Yeah. So are you muted, Kazuhisa-san?
He's
talking and no audio.
I see the border lighting up, but I don't hear anything.
Is your mic turned way down? Okay. Now that's audio.
Hello, can you hear me?
Yep.
I'm Isaku. He's now leaving and get back again.
Okay.
Just a moment, please.
We'll give it a minute to
Yeah, we're on a very tight schedule, so let's try and
catch up. Yeah.
catch up. Was he going to use somebody else's computer or something?
I think he's left the session entirely. So I need to load up the slides again.
Did he do it or did you just do it? I see.
I am doing
Okay.
it.
Sorry, can you hear me? Can you hear me?
Yes, yes.
Very sorry. I can't use I can't enable the mic. It's yes, I can't use the mic, but it's not okay. So
Okay.
Okay.
You need to go back. Yeah.
All right. Over to you.
Okay, and I'm moving into the slide. Oh, okay. So okay. So the reason why the preference from links close to the consumer is the nodes closer to the consumer are more likely to detect the latest data loss, which means it's more likely to cause a duplicate data reception. So as I mentioned, based on the allocated budget,
And this morning we had a ton of issues, so I don't know.
I'm wondering if we should jump to the in-person session and then we'll come back to the remote sessions.
Well, we have one in-person talk.
Yeah.
sorry. Can you hear me?
Yes.
Can we try
sorry.
maybe you should
One
send
more
the video.
try.
Yeah, and then also maybe turn off the video on your end for this time just to make it.
Okay. Yes.
Okay. Let's try that and see how it goes.
Okay. Okay. So the time I use a lot of time, so I want to summarize my presentation. So I actually conducted full-time implementation using CEFOR, which is an open source software platform. Everyone can freely download this source code via this URL. So I actually conducted an experimental evaluation using the prototype implementation, and we observed two performance metrics. One is a successful loss recovery ratio, and another performance metrics is a duplicate data reception ratio. And we compared our schemes with two other schemes, the baseline scheme and the existing scheme like this. So we investigated the impact of acceptable latency differences. So as we can see, the left figure, the left graph shows the successful loss recovery ratio. So our proposed scheme achieves more than 90% of successful loss recovery and higher recovery ratio compared to other schemes. And also, our proposed scheme effectively suppress duplicate data reception, especially in the case where acceptable latency is relatively high. So it means that our proposed scheme achieves a well-balanced performance according to the acceptable latency, so enabling the effective and efficient in-network loss recovery. Yes, in summary like this, and we propose in our future work, we'll develop an effective rate control scheme using this in-network retransmission scheme. Thank you so much.
Right, thank you for the talk. Are there any questions? If you have any questions, please join the queue. Okay, seems like there's no questions, so let's move on. I'll take back the control for the moment. Thank you very much, Kazuhisa-san.
Thank you.
Next talk is by Yohei Okamoto on reflexive forwarding implementation in CEFOR. For that, I need to give screen sharing control. Right. Should work as expected.
Okay.
All right.
Okay, start my presentation. Today, I'd like to talk about reflexive forwarding implementation on CEFOR. I am Yohei Okamoto from ID Corporation, working as a member of the CEFOR project. Here is an outline today's talk. We briefly explain the technical specification of reflexive forwarding and talk about the implementation in CEFOR. We then show the demo how reflexive forwarding is working on CEFOR. Reflexive forwarding uses 4 messages: trigger interest, reflexive interest, reflexive data, and trigger data. Also, trigger interest TI is forwarded based on each forwarder's FIB. Reflexive interest RI is forwarded by a reflexive name prefix R and P specified in TI. As you see in left figure, when a consumer wants push data, it sends a TI to a producer by routable name. TI includes a reflexive name prefix, which is uniquely assigned by consumer and used as the name of RI. When producer receives the Okay. RI can support chunking if necessary.
Okay, so from here, I'd like to explain some operation using CEFOR implementation. So at first, the consumer sends the trigger interest, as you see, and let's see the trigger interest has a name of abc.com/RNP ID, and RNP ID can be generated by UID, for example. And this trigger interest is forwarded to the forwarder 1, forwarder A, Then this forwarder A generates the TI bit, trigger interest bit, as general interest, and also forwarder A generates a template bit, T bit, to be referred by the reflexive interest later transmitted. So this trigger interest is forwarded toward the producer, and then producer sent back to the reflexive interest. Next, please. So this slide shows a returning packet, which is a reflexive interest. Reflexive interest is sent by producer using RNP ID. So the routable name is just excluded, and only the RNP itself is a name to be retrieved by producer. So this is something like a subscribe request. And so he sent the reflexive interest toward the consumer based on the TPIT entry. So after, for example, forwarder B receives reflexive interest RI, then he can just copy the TPIT as a regular PIT entry named RI PIT. So TPIT is actually just a reference. It doesn't use for the forwarding entry. So TPIT is just a reference to generate the RI PIT, and then the RI PIT is generated to each forwarder, and then this reflexive interest is forwarding back to the consumer. Next, please. So this slide shows the same reflexive interest, but it includes a chunking ID. So with chunking. So in that case, producers send the reflexive interest with some specified chunking number, like chunk 1, chunk 2, and so on. So the difference of the previous slide is that when we support the chunked content, then RMP TPIT, which consists of RMP ID only, RMP ID, is copied to RI PIT, but it also includes a chunk ID, like a chunk equal 1 or chunk equal 2. So for each chunking data, chunking interest, this reflexive interest is forwarded toward the consumer by generating a chunk ID on each forwarder. Okay.
Next, we will explain a pub-sub operation using SFO. This demo consists there are 3 nodes: a consumer, forwarder, and a producer. SafeNetD is a forwarding demo of the SFO component. First, a producer runs the SFO file command and wait for TI from a consumer. Then, consumer runs the save file command with a name demo1 to push data. After a consumer initiates a TI operation, TI is sent to a producer. Forwarder then creates TI PIT and TPIT. After producer received TI, it initiates a RI operation using RNP. When producer received RI, it creates RI PIT using TPIT, and the RI packet is sent to a consumer. When consumer receives RI, it immediately sends a corresponding RD. The RD is forwarded based on RI PIT. If data is chunked, RIs and RDs are transmitted repeatedly in parallel. When producer completes received RDs, it initiated a TD operation. When consumer received TD, it terminated this push operation. Today, we will show you two demonstrations. First one is a demo to push a simple small file. You can see the sequence of TI, RI, RD, and TD on the packet capture. Now, we will play the first demo video. Please look at the producer in the top right. The destination directory is empty. I'll execute the save sub file command. Next, please look at the consumer in the top left. I'll run the save file command. Then the packet transfer will begin. Please look at the bottom. You can see the TI, RI, RD, and TD packet have been exchanged. This is the RNP value. Finally, we can confirm that the producer has received the pushed text. Next one is a push operation send a large sized chunked data. We will see that RIs and RDs are transmitted many times. Now, I will play the second demo video. Similarly to the first demo, let's confirm that the producer's directory is empty. Once I run a save sub file on the producer and save sub file on the consumer, the packet flow will begin. Here is the RNP value for this session. You can see that the file has been successfully generated on the producer side. I will play the push video using VLC. As you can see, it plays without any issues. That concludes my demonstration. Thank you very much for your attention.
Thank you very much. I guess because of the screen share, there was a slight choppiness, but I trust that that is because of the screen share, not because of the actual data transmit. Does anyone have any questions? Please join the queue if you do have any using Meet Echo.
Anything?
Not seeing any comment on the Zulip either. All right, suddenly we're catching up with time after the first delay.
Good.
All right. Thank you very much. All right, let's move on to another talk. Okay, the next talk is by Kenji Kanai, ICN Service Mesh for Plug and Play ICN.
Hi, hear my voice? Can you hear my voice?
Yep.
So actually the meeting agenda, according to the meeting agenda, so maybe the next one is a information-centric wireless sensor network platform.
It changed.
Oh, yeah, I changed. Okay, okay. Sorry. Okay. So now let's start my talk.
Go on.
Hi.
Let me
Hi, thank you for this opportunity to talk with today. My name is Kenji Kanai from the Waseda University, Japan. Today, I'd like to talk to you about ICN service mesh for plug and play ICN. And this work was partly supported by the NRCT, actually the Asada-san's group. And the position of this talk is actually not about the research aimed to the improved ICN performance, but rather research conducted from the perspective on an ICN user. So here is today's content. So let me first introduce the background introduction, and then we give two topics. The first one is ICN service mesh, and the second one is deeping-based co-digital twin. So deeping is a decentralized physical infrastructure network, and co-digital twin is a co-creation of the digital twin. So I think these two words is very new. So I will talk about our vision and later. So finally, I conclude my presentation. So let me first introduction. So as you know, the blockchain technology and distributed ledger technologies are currently widely spread. So the Web3 era is coming. So in the Web3, it is said that internet structure is shifted from the centralized architecture to decentralized architecture. So this kind of the shifting, so what is the benefit in the users? So users can manage and operate their own data, not to the collecting in the platform. So the network infrastructure also follows the trend toward this kind of the decentralization. So there are the two examples. So first one is decentralized network storage, so which is currently the well-known de facto standard, namely the Internet File System. So most of the Web3 application is using this software. So in the IPFS, so broadly defined, the information-centric network is adopted as a network protocol, not a pure CCN or NDN. But IPFS is used the content identifiers or the content name to register or retrieve the data from the internet. So another example is a decentralized physical infrastructure network, deeping. So what is deeping? So deeping is aimed to build and maintain the decentralized infrastructure using the distributed ledger technologies. And the infrastructure management is actually based on the sharing economy business model. So what the realization of the deeping? So deeping is so currently the user is currently only using the network, but from the deeping, so user can join the project and they can build and manage their own infrastructure. So this is very interesting. So as you know, so the ICN is a very attractive network protocol, and we think that ICN could become a good network protocol to support the various Web3 applications. So including, of course, decentralized network storage, distributed computing, and in-network computing. And also AI is currently the very hot topic, and the AI agent or AI chaining is also the Web3 application, I think. And the other one is a trust network for DPIN and the DPIN-based co-digital twin. This is our current main activity, and I will introduce later. So, from the perspective, the user's perspective regarding ICN implementation. So there are several ICN implementations, called NDN and the CEFOR in Japan. This is in my opinion. So few implementations have reached the level of the providing application programming interface. So this means that it is very difficult to develop the application based on ICN for the developers, application developers. So developers currently must implement the ICN functionality itself in addition to the application itself. So ideally, the communication functionality should be transparent to the application, which means that the upper layers, so for example, application layer, should not be aware of the network protocol of the lower layers. In addition, and it should be possible to seamlessly replace the protocols used in existing application, like a current TCP or HTTP into the ICN. So if they are applying the ICN requiring the re-implementation, the application in the programming developers, so there is no motivation to use ICN in case, even if the ICN is very good. So the research question is it possible to implement ICN in a plug-and-play manner? So we think that we can adopt the service mesh approach. So service mesh is one of the cloud-native technologies, and it can mediate the communication between the services and resolve the operational challenges regarding the communication, like traffic control, the fault tolerance, security and access control, and the observabilities. So Istio and Envoy, this is a well-known cloud-native software, is a service mesh, de facto standard for the service mesh, but this software is primarily supports only the HTTP. So we reuse this concept, and we design ICN service mesh, aims to providing ICN functionality transparently to the applications. So our goal is to enable plug-and-play utilization of the ICN functionality, achieve the autonomous and distributed network control, and realize the trusted networks. So our research group is currently considering the architecture of the ICN service mesh. So here is a comparison of the architecture. So there are the 4 different models. So most left one is a baseline and very naive one. And this model is a service layer, application layer requiring the ICN library. And service application itself implement ICN functionalities and connect it to the network side ICN router function. So next one is straightforward way. So the service layer, application layer no longer need ICN library, but in the network side, HTTP API interface should be exposed. And the service is connected to this kind of the HTTP API to connect it to ICN router functionality. So next 2 model is sidecar or the service mesh models. So very similar to the HTTP model, but between the application layer and the network layer, there are the service mesh layer. And in this layer, we implement the ICN library to intermediate the service and the ICN router function. So the third model is, of course, a very naive model, but easy to implement the service mesh layer, because in this layer, ICN router functionality has in this layer. So most of the code is reuse the ICN library or router function. However, the service mesh layer requiring large resources to run the router functionalities. So the right one is without a router model, and the service mesh layer is no longer need router functionalities. So ICN library is directly intermediate the service and ICN router functionalities. So ICN library has exposed our own API, and ICN router functionality has also the API. So that we need to carefully design these blocks. So next slide is show the deployment strategy. So the left one is a baseline model. As I said, it is naive model. Service is ICN router is required for each services in the packaging. So there is a scalability issue because the number of services increase. ICN router needs to increase. So HTTP API model and sidecar model is very similar. And ICN router can be shared among the several services to access the HTTP server or service mesh. So, however, additional resources like HTTPS and service mesh to run the additional resources. So this is a very simple performance comparison regarding memory usage in among the 4 models. So left figure shows memory usage comparison results in case of the 2 services deployment scenario. So left line is the baseline, and green and the yellow bar is the memory usage of ICN router or the sidecar. From this result, you can see that you can understand that the sidecar model can reduce the memory usage approximately 0.6 to the 0.8 times compared to the baseline model. And compared to the HTTP model, so as I said, HTTP resources is very needed. So the router functionality required in memory 9 times increased compared to the sidecar model. So the right figure shows memory usage comparison results in case of the 1, 2, 3 services deployment scenarios. So from these results, sidecar model, especially the without a router case, the reducing 0.8 times the memory usage compared to the baseline model. So the another result is this is the content retrieval time. The HTTP's code implementation is very mature. So the performance is HTTP is good. However, the sidecar model is also the comparable is a baseline. So we can think that the service mesh has a comparable performance with the baseline, but lesser memory usage. Okay, so this is ICN service mesh, and we move on the next topic, deepin-based co-digital twin. So this work is also supported by the LCT. So what is the motivation is we collect and update and share the latest digital twin data effectively. So here is our problem statement. So digital twin, so especially not the network digital twin, but a city level digital twin is a critical enabling technology to construct the smart city that helps improve the citizens' lives and the quality of life. So currently, many research projects regarding the digital replica city are ongoing in the worldwide. However, most of the project is only focusing on the how to create a city model. So there is no mechanism how to maintain a sustainable and up-to-date digital twin on large scale. So we think that there is a lack of mechanism to involve the various key players, such as the data, how to join the data providers or service providers, application developers in this project. So we think that the mechanism, the ecosystem is essential for constructing the digital replica city and producing the various city replications. So our approach is very simple. So there are 3 points. So first point is city residents play an important role as a data provider. So as you know, most of people have a smartphone, and the smartphone has a very powerful sensing devices. So it equips many sensors and the image or video, capturing the image or video, and even 3D data using the LiDAR. So the smartphone or the holding the city residents can be play as a data provider. And they collected data and selling data. So another second point is we doesn't think that without a third-party data provider or the data broker, the provided data is directly traded to the service provider. And the third point is when the service provider buy the data provided by the resident, this kind of the service provider pay the reward to the resident. So this is kind of the incentive mechanism. And this incentive mechanism would keep the resident collected data and update data. So here is our vision. So from this circulation is to keep the up-to-date digital twin by the participant licensing. So this is our vision. So we done a feasibility test of the digital twin. We collected 3D point cloud data using iPad LiDAR sensor, and a very few number of people, just 6 participants, with collected their 3D data, their own devices. And in the system side, this data is merged, and one large 3D, creating a large 3D map. So this is a comparison. So left one is our created 3D map, and the middle one is a map provided by the OpenStreetMap, and the right one is a local floor map. So you can confirm that, visually confirm that our co-created 3D map has a nearly equivalent accuracy to existing maps. So in the system side, the system is currently running on NRCT's testbed. So the system architecture is very straightforward. So we define the regional server. So regional server has on-chain storage and off-chain storage. So on-chain storage is for the blockchains, using the blockchain technologies, 2 layers blockchain technologies, and storing layer 1 blockchain store the transaction information, and the layer 2 blockchain is for the smart contract for the reward distribution. In the off-chain side, we use IPFS to save the 3D data itself. So data setter is accessing this regional server through the API to upload and sell their data. And the data buyer side is accessing the front-end application to check the data catalog and purchase the data provided by the data provider. So this slide shows deployment strategy, and the point is a data storage network and the metadata storage network, and the system endpoint is in the network edge, or let's say the geographically distributed these nodes. And again, regional server is has a role to intermediate between the users and the storage network, this kind of the storage networks. So the smartphone is no longer need to installing the IPFS or other specific application, just using the website or HTTP. So actually, we are running this prototype system, but through the feasibility test, we have found 2 technical issues. So issue 1 is a very straightforward security issue. So as you know, we using IPFS. So IPFS is used the content identifier to register or retrieve the data. So if the content identifier, CID, is registered with IPFS, is leaked to the outside, so data can be freely accessed. And also we have no encryption, content encryption. So someone who obtains it, so easy to decode it. So this is a very critical issue for the purpose of the buying and selling the content. So second issue is storage network performance. So the content persistency and effective storage utilization. So maybe the time is running out, so we speed up. To deal with our issues. So we are currently collaborating with NICT, and we using the NICT assets, namely the UC-INC. So user-centric in-network caching. So detailed features of the UC-INC is please see the IEEE ICC paper. But there are the 3 key features. So first one is the security and privacy. So UC-INC adopts the ciphertext policy attribute-based encryption. And the second one is there is geographical limitation capability. So cache data in routers within a permitted area and cross to authorization users. So this offers efficient data transfer and high performance data download. So the third one is availability, high data availability by using the caching data in multiple intermediate routers using the ICN technologies. So we using this UC-INC and ICN service mesh to solving this issue 1 and the issue 2 and issue 3, the implementation challenges. So remaining time, we focusing on the how to using the ICN to deal with the issue 2. So actually, this is a early stage research. So we focus in on IPFS routing problem. So IPFS data discovery has two searching steps based on the Kademlia algorithm. So first step is searching for the PID, who has this content. Next one is searching for the connection information. So PID is information like IP address. So in the IPFS, pair of the IPFS and PID as a content IG are managed in a table called the provider record. And the provider records are exchanged only between the neighboring nodes. So idea is very simple. So how about replacing from the Kademlia to ICN to distribute it the provider record? So to do so, IPFS data discovery can achieve only one step. So ICN routing table enables directly discovering the provider records within the network. So here is a small test result we use on a test network topology, and we compare in the original IPFS and the ICN IPFS. So from this result, the ICN-based IPFS is a significant improvement, both content retrieval and content publication. So from our next step is currently redundant using in-network cache. So how to use effective use of in-network caching, like caching the provider records and also the content itself, and also the how to integrate with UC-INC. So this is our next step, and yeah, here is conclude my presentation. Thank you for the attention.
Thank you. Just about enough time for maybe 2 questions. Anyone from the room on site?
Wow,
Right.
these are very clear presentations then. That's great.
Maybe I'll join a queue myself and answer one question. Ask one question. So, in the earlier part of the talk, one of the conversations was about having a HTTP API and how that had some cost in terms of enabling that. I suspect, like in the pathway to sort of enabling ICN-based wider network, would you say this HTTP API gateway as a sort of a worthwhile, potentially a worthwhile sort of cost to sort of bridge that time between sort of where we are right now and then to sort of move towards the more ICN-based transport underneath, I guess?
So, sorry. I cannot catch up the point of your question.
So in short, would you say that this sort of like cost is perhaps worth taking to sort of have it as a sort of a transition period while, in between the sort of the to bridge the non-ICN network and to ICN network.
Yeah. So at the beginning of the motivation to develop the ICN service mesh is we utilize not changing the entire network, but in the, for example, cloud native area. So the pod network or between the microservice communication, we change the HTTP into the ICN. This is our motivation. So in that motivation, maybe not so costly if we provided the ICN service mesh in the software. Yeah.
Okay, any other questions? All right, thank you very much. I think the time managed to catch up on us now, so we shall now swiftly move on to the next talk. I'll take the slide control. Thank you very much.
Thank you very much.
So the next is
wireless sensor platform.
Yep. Information-Centric Wireless Sensor Network. Yep. All right.
Mori-san, we need to give you the slides.
Yes. Are you joined on the Meet app?
Yes. Camera. これかな?
I see. Yep.
Oh, there he is.
Okay. Right, I've passed over the controls, so yep, floor is yours.
Okay, so thank you for your kind introduction. So my name is Shintaro Mori from Fukuoka University, Japan. So today I'm going to talk about this title, and today, I'd like to explain information-centric wireless sensor network. So, in my research theme is to introduce ICN technology into the wireless communication and wireless network. So today I'd like to provide some effectiveness of the information-centric sensor network and demonstration of the feasibility of the scheme. So everyone knows IoT framework are widely used, and the platform is shifted from cloud to edge node. So in this situation, the data and some function are constructed based on distributed and decentralized. So to use the wire sensor network is very important technology, I think, and to adapt the ICN technology into wire sensor network. Information-centric wire sensor network can improve efficiency, latency, and energy consumption due to caching mechanism. And in another feature of ICN is abstraction. So different from wire network, wireless communication system typically heterogeneous. Many protocols exist. So to use ICN technology to overlay the low layer, the protocol can abstract and easy to use for my wireless communication researcher or another field, I think. So the next shows the motivation of ICN and wire sensor network. So we would like to introduce ICN into wire sensor network and to implement this system as an ICN platform, we use CEFOL. So this slide shows an effective caching scheme. Different from the wired network, wireless communication and wireless network system has a significant feature of overhearing. Overhearing is the node along the routing path can also obtain the transmitted data. So to use this phenomena, the ICWSN can achieve off-path caching without any particular mechanism. And as shown in this simulation result, the ICWSN can boost the caching mechanism. So to use ICN and caching mechanism, the system can reduce energy consumption. So everyone knows wireless sensor network has strictly hardware limitation, in particular battery resource and calculation capacity and wireless spectrum. So to apply the ICN into wireless sensor network as a caching mechanism, the ICWSN can improve these traditional issue. This slide shows some computer simulation result. The proposed method is ICWSN, and conventional scheme is not to use without use caching mechanism. So to use ICWSN, the system can reduce the energy consumption. So based on the previous fundamental research, we construct some prototype device and prototype network. So of course, the sensor nodes show the left side photo, and the network structure is right hand side. Of course, we use CEFOL as an ICN platform in the system, and sorry. Okay, to use ICN mechanism, the first data retrieve is so high expensive, so latency and high jitter and low throughput. But after second time, thanks to the caching mechanism of ICN, we can dramatically improve the network system. On the other hand, to shift from the conventional host-centric to ICN, there are some conventional and traditional systems coexisted, I think. So to improve the situation, we equipped the gateway to exchange the compatibility, the API-based traditional scheme to ICN, and we can guarantee the compatibility to the ICN scheme. Okay, so based on the previous all research, I'd like to construct the new platform for smart city as a service. In particular, I'd like to construct the millimeter wave information-centric wireless sensor network platform for supporting a new ecosystem. So in beyond 5G and 6G wireless communication system, the wireless radio frequency and spectrum is so hungry. So in the research field of beyond 5G or 6G is to shift the higher frequency. So to demonstrate the feasibility of the information-centric wireless sensor network on the high frequency spectrum, such as millimeter wave. So we construct the test field and we some experiment and to demonstrate the effectiveness. As shown in this photo, we constructed two test fields and connected to each other, and we conduct experiment. One is on the ground, and the other is a non-terrestrial environment. In the beyond 5G network is alternatively research topic is aerial node, aerial base station. So to demonstrate such aerial base station environment, I conduct the experiment, the ICN scheme, ICWSN on the such a non-terrestrial environment, of course, millimeter wave communications. This is some experimental result. We can obtain the throughput, and we can demonstrate some video streaming on the air-to-ground communication. And of course, we have to consider some UAV, the condition, but they are very technically and hard to demonstrate. So instead of such situation, in multi-hop experiment, we use smartphone, and we can also demonstrate the air-to-air wireless communication, of course, information-centric network environment. So this slide shows another test result. The figure side is a network model of the implemented test network, and this sensor node is a publisher, and the end user is subscriber, and there are three network sections. One is a cellular network, but so low bandwidth, and another is a wired network, and a very high speed and very wide band communication. So to use ICN and into the IoT platform, the data, when the user retrieves the data, the average throughput is low at the first time, but after second time is can improve the throughput because of the cache data is located on the wired network area, so throughput can improve. So another scenario is in my research, we conduct a smart agriculture project for deployment of our scheme. There are three solutions and topic: remote monitoring of greenhouse and automatic harvesting robot and security and pest prevention system for the farm. In the previous project, the network structure is a very traditional and conventional scheme, but there are some technical issue of the conventional network structure. So I think this issue can improve to use information-centric wireless sensor network. For example, the conventional scheme in the conventional sensing data must be continuously sent to the cloud server, but to use ICN and ICWSN, we can achieve higher efficiency by pull-based design to ICN mechanism. So this slide shows a demonstration result of the strawberry harvest robot. Of course, the robot is require strict throughput and latency, but the traditional framework are still issue to requirement of this strict requirement. So I think and I hope to use ICN and ICWSN, we can improve this and remove the issue, I think. Oh, 時間が。And so based on this research project and research work, now I plan to conduct a new project, information-centric wireless sensor network for deployment in the smart agriculture. The overview of the project are shown in this slide, and the research item are shown in the following slide. One is real-time data transmission system for robot or real-time data surveillance system in the greenhouse. And another is communication control in ICWS using AI, such as improve the efficiency of the wireless communication and wireless network system. Okay, finally, I conclude this presentation, and now ongoing work and contribution of future wireless network of my millimeter wave information-centric networking and wireless sensor network, and the last is finally is future works. Okay, that's all my presentation. Thank you.
Thank you very much. That was actually quite cool. Does anyone have any questions? I put myself in the queue just to sort of start the queue, but okay. So actually, I'm going to use my chair privilege, and I'll go ahead. You mentioned earlier that the overhearing can be utilized to pre-cache the data. Could you talk a little bit more about how that's done at the sort of the network layer perspective, sort of how that's actually happening in terms of like name and stuff?
Sorry, what is the question? Sorry.
So in short, how does the overhearing effect utilized in the context of the network layer perspective, like in terms of names and data context? How does that work?
Yes, that's very important, because wireless communication system is broadcast-based networking, I know. But network layer is unicast-based, but ICN layer is also broadcast or flattening. So the network is different between ICN layer and physical and MAC layer. So this is challenging to implement the overhearing and this off-casting mechanism. I just only I just demonstrate the some result in terms of physical and low layer only, but that is very important and significant term of the implement, I think. Yes.
I'll be curious to see how the how the caching mechanism itself adapts to this, to utilize the overhearing phenomena, I guess. As
yeah,
I would like to see that happen in the future.
Yes, overhearing is specific in wireless network. I think wireless network is not overhearing. I think. Yeah.
Hi, this is Dave. I have a kind of a related question, but from the slightly different point of view, which is there have been previous efforts to use opportunistic caching on a broadcast channel with ICN. And the hard problem seemed at least then to be if you have multiple of these cached versions on the same broadcast channel, how do you decide which one actually responds to the request as opposed to all of them trying to answer and clogging the channel? Have you given any thought to how you address that problem? Or did you not understand the question?
Sorry, what? Sorry, what is
Well, I can take the question offline with you. I'll just send you some email rather than taking up everybody's time. So I'm sure you have a good answer. I just like to see how you've approached the problem. Thanks.
Okay.
Yes. Okay, thank you.
We'll discuss this further over the mailing list, I guess. All right. Thank you. All right. Thank you very much. Do we have Hongbin in the room?
I could not find him in the participants list. I direct chatted with Dirk.
Hongbin.
Is he in the room?
Yes. Okay. So it turns out it's actually not Hongbin giving the presentation.
Who is?
You have to introduce yourself.
Sorry, let me take.
Okay, we are ready.
Hang on. Let me switch the slides to.
We have to hand. Hand the clicker to Dirk.
Yes. Why not? Let's pass the slide control to Dirk.
Yeah.
Okay.
Okay. So good afternoon, everyone. My name is Shan Zhang. Okay. Thank you. So good afternoon, everyone. My name is Shan Zhang, and I'm from Beihang University. I work in a research group which focuses on new network architecture for heterogeneous network, the integration of computing and networking. And the research group is led by Professor Hongbin Luo. I'm very honored to be here to share our recent work, which is Hyper ICN architecture for computing power network in Edge. I cannot go to the next slide. Yeah, it doesn't work.
Doug, you have control.
Yeah, it doesn't work. Are you sure? So the clicker needs to have control.
Oh, okay. So is it the slides clicker that needs? Okay.
Yeah.
Okay.
Can you try now?
Oh yeah, good. So let me go briefly review the background. We all know that most of the data is generated by the devices at the network edge. And if we look at the devices varies a lot. there are many devices like cameras, sensors, machines, IoT type machines, which generate lots of data, but they do not have capability to deal with the data. Meanwhile, there are also some devices like the intelligent cars. They are usually equipped with abundant computing resource to process their data. So if we can let the devices find each other and collaborate with each other, we can unlock the underutilized computing power to deal with the data at the edge. And that's the, oh, I'm sorry, there are something with the slides. And thus the computing efficiency can be greatly improved by 30%, according to recent research. But the thing is, if we open our cell phone and we can find the devices we can connect it, but we don't know what they can do and what's their computing power. So we need a new architecture to support such ideal figure. There are already some works on this path, including IP-based solution and ICN-based solution. The IP-based solution usually adopt application layer or proxies to manage the computing resource and help the end devices to select the appropriate server to provide service. But the thing is, then the network layer will help to build an end-to-end connection, the path to transmit the data. This solution works good if the network condition is good. But at the network edge, devices may move and the wireless connection may change. It may happen that the proxy may select a weakly connected server with sufficient computing power. That because the proxy do not know how the network condition is. But if we look at the ICN-based solution, ICN architecture naturally couple routing and addressing together. It helps to find the server while building the path. So it's promising to find a good server with acceptable connection. That's why we go with the ICN-based architecture. Let me go to the 3 fundamental problems we met when we try to figure out this architecture. The first problem is the management of heterogeneous resources. When we try to complete a computing task, we need to find the source data, we need to find a device with the container environment, and also with sufficient computing power. That means we need heterogeneous resources. And if we look at these heterogeneous resources, the computing power is very different. For example, if I want to talk to Professor Oren, I have to talk to Professor Oren's devices, even if he's very far away, because that's unique. But if I want to complete a computing task, I won't want to find Professor Oren. I want to find any device which is in proximity and provide sufficient compute power. That's enough. So naturally, the computing power is not unique, and it's enough for us to maintain local information. So the problem is how we can maintain these different object information considering their different properties at a lower cost. That's a basic problem for the control layer design. And the second problem is how we can support both server finding and result returning. So when we try to find a server, it's good for us to use ICN because we want to find the appropriate destination and we want to find the appropriate path. That's the way how ICN works. But after the computing task is accomplished, we want the server to push the data back to the user. At this time, it's more efficient to directly push. But actually, after such a computation time and uncertain time, the reverse path may not work. especially at the network edge for user mobility and wireless communication or wireless connection. So how we can rebuild the path fast and efficiently in this dynamic environment, that's our second problem. The third problem is how we can support dependent computing tasks. So we know that the end devices and the servers at the edge are usually computation or resource constrained compared with the data center. So it happens we need multiple devices or multiple servers to help to support one task together. The current ICN architecture only support single service or content retrieval. So how we can decompose the task and how we can form this collaboration relationship. That's our third problem. Following the third problem, we design our HiCom architecture. The first design is that we propose an integrated but different control plan to manage the resources of heterogeneous resources. We keep the SID, NID, IP address. Specifically, we attach the computing power information to the node identifier. The reason why we use multiple dimensional namespace is for three aspects. Firstly, in this way, we can keep a global view of services and devices distribution. And for the second aspect, we can simplify or truncate the computing power information in the spatial domain based on their mapping relationship to the NID and IP. And the third reason is that we can also support different routing patterns during the server finding phase and the result returning phase. This here shows the details. So as I mentioned, when I want to find a server, we do the addressing and the routing together, because for this stage, the destination is pending. We don't know which server should take the task. But for the result returning, we know exactly who should take the data as the user. In this phase, we believe the IP-based push routing is more efficient. So we support both routing patterns by keeping the multi-domain namespace. And specifically, we keep the mapping relationship between the SID, IP, and NID. The third design is about how to support the dependable task. Firstly, we use the directional asynchronous graph-based architecture to support the description of a task. After this request is raised, we will try to figure out what's the critical path and the critical subtask. And we first find the appropriate server for the critical subtask. And from this subtask, we decompose the graph into multiple graphs. The forwarding tasks may form different graphs, wherein the critical path or the selected server will act as a final user. And for the forwarding tasks, the selected server will behave as the source data or source node. In this way, we can decompose the whole task into in a recursive way. And finally, build a collaboration relationship. So that's the main design aspect of the HiCom architecture. Actually, the HiCom architecture borrowed many ideas from computing first network, CFN. And we share lots of similarities. For example, the whole design object, the namespace, and the task scheduling aspect. But we do focus on three aspects for the new design. First is that we find the different property of computing power, which is not unique, and we cannot just name it by using NID or SID. And the second aspect is that we keep the IP address to speed up the result returning in the push manner. And the third difference is that with this task decomposition method, we can help the multiple devices to collaborate. And in this collaboration, the status synchronization is simplified. For the CFN architecture, there usually is a centralized controller to synchronize the status of all involved servers. But in our architecture, after the decomposition, the server node only need to talk with the preceding ones. We realize our architecture as a prototype. So we have the resource manager node and the server node. The resource manager is implemented with the control plane functions, and the servers handle the data plane functions. We built the platform shown as the bottom figure. We have one user raising video analytic request. We have two resource manager representing different areas, and the two resource manager can access different servers to handle the computing task. Meanwhile, the resource manager will maintain the status of the servers. In our experiment, we emulate different cases, including when the user moves from one resource manager to another one, when the traffic load of a server decreases, and when the server disconnects. The experiment's results show that with these different environment dynamics, our proposed HiCom architecture can adapt to the change very fast and always switch to the best server with good enough connection. So that's basically for my talk today. Actually, this is just ongoing work. There are many opening issues under this architecture. For example, how we should model the computing power and integrate this resource information based on the network topology. And for example, how we can depict as AI agent comes on, which is a very hot topic, maybe the computing pattern will change, not like only human or only machine, but a human and machine integrated way. So in that sense, how we should represent the computing request and how we can decompose the request by like language model and how to support this kind of complex task. Besides, there are some security concerns about this zero trust environment, how we can make it robust and fault tolerant. Thanks again for Professor Kuster and Professor Oren's invitation. And thank you for your listening. Thank you.
All right, thank you very much. We have Rod on queue.
Hi, Rod Van Meter. So thanks for the presentation. I think this is really fascinating work. It's a great topic. I've been interested in topics like this for a long time, but never really worked on them very directly. There are lots of questions around this, and I'm sure you've answered a lot of them in your research papers and related topics. So forgive me if they're sort of basic, but if you mentioned anything about maintaining versions of software as the computation moves around the network, I missed that. Do you have some system for guaranteeing that you have the right piece of code at the node where it's actually being run?
Yeah. As I mentioned, we have built the prototype.
Uh-huh.
The machines, as the figure in the middle, we build the resource management node and the server node. For the resource management node, it is responsible to gather the status information of the servers, like the distribution of all SID, NID, and the distribution of computing power of different servers. That's what the resource manager do. And for the servers, it has container-based environment and is responsible to deal with users' computing requests, finally.
Okay.
I'm not sure if this is the question.
It does. It's certainly headed in the right direction. I would probably have a lot of more detailed questions about it, but let me ask another big picture question. How much have you gone back and looked at some of the distributed systems research that was done in the 1980s and 1990s, the old the work on Amoeba and V and Sprite and those things that old people like me try to teach to our students sometimes?
Yeah, thank you. Thank you for your kind reminder. Yes, we did some work on the previous research, and we actually find some architectures have the very similar goal. And actually, the time is kind of limited, and that didn't go to much details. Yeah, there are some architectures have the similar goal, and let me see. That's a really very good question. So what we do, I think if I divide the existing work roughly, forgive me if I'm wrong. So some work focus on the distributed computing architecture. It's on the data plane. According to my understanding, it has a logically centralized control plane, usually implemented as a physical on a physical node. That's one path, and there are also some works try to totally distribute the architecture, and we find one of them is dispersed computing, which is maybe 10 years ago, and there are some work. There are some very details difference compared with our work. For example, they are built on IP-based architecture. For example, if they support dependable task, they will use the segmented routing topology. So only some nodes have the function to make decision, and the user can only go to those nodes. What we do is we, based on the ICN architecture, want to simplify this function and totally decompose these resource manage function to each node to make the system more flexible. Yeah, as I mentioned, it's just a ongoing work. We are also trying to find more details, but to my understanding, if we make it more distributed, including the control plane, it will provide more flexibility at the network edge to the end devices. That's our focus.
Thanks. This looks like really good work. This is one of the most interesting things I've seen lately. Thanks.
Thank you. Thank you.
Got more questions? We can't hear you.
Sorry. Right. I see that there's a lot of indirection and mapping going on. I was wondering if you had any thoughts or intuition about overheads of managing these multiple identifiers being mapped to one to the other, and then sort of having to switch between different paradigms.
Good idea. That's not the very good question, actually. And we have been asked for the same question by industry as well. Yeah. I think we finally will go to a more simplified namespace. That's my envision, actually. But for the beginning, we are not sure which dimension should we choose finally. So at the beginning, we keep all the names and want to find the relationship between different names and try to figure out which should be kept finally.
Thank you.
Thank you.
Doug?
Yeah, I also have a question. So thanks very much. Really interesting talk. Good topic. I wanted to ask you, can you explain a bit more, so why you chose this split between using the IP addresses and the names in the system? So why do you really need IP addresses in that system?
Oh, thank you. Thank you for the question. Actually, for two reasons. The first reason is that I mentioned we noticed the computing power is quite different. It's a kind of resource we care about, sufficient resource, not a unique resource. Yeah, so we cannot not just name it. So the problem is how which domain we should attach this resource to. Our current solution is to attach this status to the NID, the node, because that's the substantial aspect. But if we only attach to the node moves. And yeah, and also we care about the computing power in proximity. So we also need the location information. That's why we keep the IP. And the second reason is I mentioned when we try to send back the computing result, push it is the direct way. That's another benefit. That's why we keep IP. And I also noticed that for the IP community, the IP6, they also use the Anycast address to represent the service. So according to my understanding, maybe these two names will finally merge to form a larger namespace. But actually, I didn't. We are still ongoing this aspect. Thank you.
Okay, great. I think that could indeed be maybe future work to sort out. So what are the requirements on mapping the names to dynamically changing topologies, and what are different ways to achieving it? Yeah, I'm hoping we can get an update on your work in the future.
Thank you.
Thanks.
Thank you.
Thank you very much. Excellent. Right. I think that brings us to the end.
Very good time management for the speakers. Thank you so much.
Thank you very much indeed. Let me take a moment to take back the control. And let me take a moment to also thank all of the speakers today. Do we need to go back to the? No.
Well, just to mention what's happening coming up.
Yes, chair slide. Confirm my selection. Right. Okay. Right.
So let me just come in for a second. There should be one more thing on this list. The submission deadline for ICNP, the International Conference on Network Protocols, is coming up in probably a little over a month. And there is an ICN track in the call for papers for that conference. And I'm the area chair. So it'd be really nice if we could see some more ICN papers making its way into that conference. It is a tier 1 conference, and you get a lot of points for getting papers in. So if you have something that you're looking for submitting and didn't meet the SIGCOMM deadline or the impending NSDI deadline, ICNP is a really good conference for showcasing your work.
All right. Excellent.
And then beyond that, we should start planning for another meeting in Vienna. Hopefully we'll be able to see more progress and maybe some follow-ups for some of the in-progress work that we've heard about at this meeting that may have gotten a lot further along. They're in the reflexive forwarding work and in the wireless space using ICN for opportunistic caching. So please stay tuned, and we appreciate everyone's participation today.
Doug, did you want to say something?
Oh, yes,
Yeah,
from
thanks very much.
the IETF chair. Thank you.
Thanks very much for chairing the session so well, and wish you a nice rest of the day in Tokyo.
Thank you very much.
See you soon.
See you soon.
Oh, Win, good to see you. Good to see you. Oh, I didn't know. Yeah, no, it's really good. Really good. I come down in a moment.